One way of dealing with this conservative nature of depth-limited search is to improve upon the arbitrary zero value returned for non-terminal states. In heuristic search, this is accomplished by applying a heuristic evaluation function to non-terminal states. Such functions are based on features of states, and so they can be computed without examining the entire game tree. The implementation of fixed depth heuristic search is easy. At the top here we have the implementation of simple depth limited search that we saw earlier. And at the bottom we have the implementation of heuristic fixed depth search. The only difference is that we've replaced the default value of 0 with the result of calling the evaluation subroutine evalFun on the state being considered whenever the depth limit's exceeded. Tough part of the implementation is figuring out how to evaluate non-terminal states. Fortunately, examples of heuristic functions are bound. For example, in chess, we often use piece count to compare states, with the idea that in the absence of immediate threats, having more material is generally better than having less material. And similarly, we sometimes use board control, with the idea that having control of the center of the board is more valuable than controlling the edges or the corners of the board. The downside of using heuristic functions is that they're not necessarily guaranteed to be successful. They may work in many cases, but they can occasionally fail. This happens, for example, in chess when a player is checkmated even though he has more material and better board control. Still, games often admit heuristics that are useful in the sense that they work more often than not. While for specific games, such as chess, programmers are able to build in these valuation functions, this is unfortunately not possible for general game playing, since the rules of the game are not known in advance. Rather, the game player itself must analyze the game in order to find useful evaluation functions. Now, in an upcoming lesson, we'll discuss how to find such heuristics automatically. That said, there are some heuristics for game playing that have arguable merit across all games. And in this section, we're going to examine some of these heuristics. And along the way, we'll show how to build a game player that utilizes these heuristics. Okay, mobility is one such heuristic. Mobility is a measure of the number of things a player can do. It's going to be the number of actions available in a given state, or number of actions available in steps away from the given state. Or it could be the number of states reachable within n steps from the given state. I note that that can be different from the number of actions, since sometimes different actions can lead to the same state. A simple implementation of the mobility heuristic shown here. The method simply computes the number of actions that are legal in the given state and returns as value the percentage of all possible actions represented by this set of legal actions. That's all possible actions in all states. Focus is another heuristic. It's the opposite of mobility. It's a measure of the narrowness of the search space. Sometimes it's good to focus to cut down on the number of possibilities to be considered. Usually it's better to restrict an opponent's moves rather than keeping one's own, so that one keeps one's own options open. And a simple implementation of the focus heuristic can be implemented as shown here. It's a dual of mobility. Again, we divide the number of legal actions in a state by the total number of actions available in any state, but rather than returning that percentage as a result, we subtract it from 100. Goal proximity is another heuristic, a little bit different from the previous two. It's a measure of how similar a given state is to a desirable goal terminal state. Now, the various ways this can be computed. One common method is to count how many propositions are true in the current state and are also true in a terminal state with sufficient utility. The difficulty of implementing this method, unfortunately, is that it is obtaining the set of desirable terminal states with which the current state can be compared. It's not so easy. Another alternative is to use the goal value of a state as a measure of progress toward the goal, with the idea being that the goal value of a non-terminal state, even though it's not terminal, however, the higher it is, the closer one is to the actual goal. Of course, this is not always true. However, in many games, the goal values are indeed monotonic, meaning that the values do increase with proximity to the goal. If you're trying to get out of a cave and you see some light down one corridor and not down the other, you might want to go to the one that has light. Moreover, it's sometimes possible to compute this by simple examination of the game description using methods which we can describe in the later lessons. Now, none of these heuristics is guaranteed to work in all games, but all have strengths in some games. To deal with this fact, some designers of GGP players have opted to use a weighted combination of heuristics in place of a single heuristic. The equation shown here is a typical formula. Each Fi here is a heuristic function, such as mobility or focus or goal proximity, and Wi is the corresponding weight. Of course, there's no way of knowing in advance what the weight should be, but sometimes playing a few instances of the game, for example during the start clock of the game, can suggest weights for the various heuristics. As mentioned earlier, depth-limited search is not guaranteed to succeed in all cases. Failing is never good. However, it's particularly embarrassing in situations where just a little more search would have revealed significant changes in the player's circumstances, for better or worse. In the research literature, this is often called a horizon problem. As an example, consider chess, a situation where the players are exchanging pieces, with white capturing black's pieces and vice versa. Now imagine cutting off the search at an arbitrary depth, say 2 captures each. At this point, white might believe it has an advantage, since it has more material. However, if the very next move by black is a capture of the white queen, this evaluation could be misleading. A common solution to this problem is to forego the fixed depth limit in favor of one that is itself dependent on the current state of the affairs, searching deeper in some areas of the tree, searching less deep in other areas of the tree. Here's an implementation of a variable, what's called variable depth heuristic search. This version of max score differs from fixed depth heuristic search in that there is a subroutine here called expfun that is called to determine whether the current state and or depth meets an appropriate condition. If so, the tree expansion continues. Otherwise, the player terminates the expansion and simply returns the result of applying its evaluation function to the non-terminal state. The challenge in variable depth search is finding an appropriate definition for expfun. One common technique is to focus on differentials of heuristic functions. For example, a significant change in mobility or goal proximity might indicate that further search is warranted, whereas actions that do not lead to dramatic changes might be less important. In chess, a good example of this is to look for what's called quiescence, and that is a state where there are no immediate captures.